Guys, good morning to all of you. Welcome to another session. Today in this session we'll be covering nuclear force as well as Deuteron problem. So both of these topics are small topics, but combiningly it becomes a big topic, and these two topics are very important for you. You can expect a question GATE exam or probably in NET exam as well. So we'll cover this. Before I start, let me know if everything is all right, then we'll start. Give me a moment. Okay, I hope everything is all right, so we can start the session. Okay, so before I start, let me tell you one thing for this. Okay, so those students who are currently enrolled in the batch course, let me tell you, the live classes which we do every day on 7:30 AM, that will continue as usual. But as we have less time, what we'll be doing, we'll target to cover those topics or those lectures first which are most important for your examination. Okay, so I have selected, let's say, 100 topics for you which are most important, and those 100 topics are picked up in such a way that it is, or you can say, almost 70 to 75% of the whole syllabus. Okay, so if any student only cover those 100 topics, then that is also sufficient to crack JRF. But as this is a batch course, so we are covering it completely. Now, because of the limitation of time, we'll cover those 100 topics first, then we'll go for this as usual detailed course. Okay, those topics are also covered in detail, so don't worry, don't think that those topics are covered in a crass way. Those topics are covered in a detailed way, but not all the topics have been covered, only the most important topics have been covered. So if you see in your course folder, in classical mechanics, quantum mechanics, electromagnetic theory, and one lecture, I think, from electronics and experimental methods have been added. So what you can do, you will attend the live classes in the morning, okay, in the usual manner, whatever we do, and in the meantime, maybe in the remaining time of the day, you can cover 1 or 2 lectures, okay, depending on the length of the lectures. You can see some of the lectures maybe 1 hour, 2 hour, 3 hour, up to 4 hours lecture is also there, I think. So you can cover maybe 1 or 2 lectures from those are pre-recorded, so you can cover them in the remaining time, okay, so that you can maximize in covering the syllabus. Okay, any question? Ajay, Harry? And also start giving the test series. You have been added to the test series, so start giving the test series, and at any problem, if you face any difficulty, you can let me know. Okay, I hope everything is all right. Let's move on. So before jumping into the nuclear force, let me cover a very important topic: cross section of a nuclear reaction. We have already mentioned about this cross section, but once again we'll do it. Cross section of a nuclear reaction. What do you understand by cross section? Cross section basically gives you the probability of occurrence of a nuclear reaction. So it is symbolized by this symbol sigma. It has the unit of area, meter square. In terms of burn also it is represented. 1 burn is equals to 10 to the power minus 28 meter square, or 10 to the power minus 24 centimeter square. So what is this cross section? So cross section gives the quantitative measure quantitative measure of probability of occurrence of a nuclear reaction. Okay, now let's say we have some target. We have some target in this form. Now target means it will have target nucleus. So the nucleus are distributed in such a way. So many nucleus are there. I am just showing only a few of them. N number of particle is incident on this target in this way. These are like the projectile. So this projectile will undergo collision with this target nuclei. Let's say this is delta x, and total n number of particles are sent. So let us write this thing, what has been done here. So let a parallel beam, of n particles, n monoenergetic particles, be incident per unit time normally. You see, they have been incident normally on a target foil. Of surface area A and thickness delta x. So what is the volume? Look, volume means what? Meter cube. Meter cube is consisted of meter square and meter. Meter square is the area, meter is the length. So area into length, if you multiply, you get a volume. Okay. Let's say is having n nuclei per unit volume. So in 1 meter cube volume, there are n number of nuclei. Now, you see, if you send n number of particles, monoenergetic particles, all the n number of particles will not interact, because it will depend upon how many numbers of nuclei present. If less number of nuclei are present, then the number of collision or number of interaction will be less, and if there are more number of nuclei, then number of interaction or number of collisions will be more. Okay, so let's say delta n is the number. Delta n of nuclei, they are undergoing nuclear reaction. Look, let's say you have sent 1000 monoenergetic particles, and let's say in the number of nuclei, I'm just giving an example. Let's say 50 nuclei are there in this target foil. So obviously all these 1000 monoenergetic particles will not be able to have the reaction. Now instead of 50, let's say if there are 500 number of nuclei, then there will be more chances for these monoenergetic particles to have nuclear reaction. If there are, let's say, 10,000 number of nuclei, then the probability of occurrence will be more. So the number delta n of nuclei in the foil containing undergoing the nuclear reaction will be proportional to what may be the factors on which this number of collisions or number of nuclear reaction will depend on. Number one, look, if you are sending, let's say, here 50 monoenergetic particles, and then there will be only 50 reactions or 50 collisions maximum. So it depends upon the intensity. Number one depends upon the intensity of the beam. Intensity of the beam, intensity of the beam means what? More number of beams you send, then that will be more intense. The intensity of the beam is the first. And what is the number? What are the number of nuclei inside this foil? Number two, the number of target nuclei. Contained in the foil. Okay. Just a moment, I think थोड़ा सा light का issue है. Now, you know, when the nuclei undergoes nuclear reaction, what is the process called? Transmutation, right? So we can say, what is the number of nuclei transmuted? So two factors, intensity and number of nuclei in the foil. But you can see intensity. What is the intensity? Intensity of the beam. Look, n number of nuclei, so it will be n by a. This will be the intensity. Because n number of nuclei, here time is also there, but it is per unit time, so that is why only a is coming. It is like, what is intensity? Intensity you can understand in this way: number of particle incident per unit area per unit time. Okay, so n by a into t. Here t is 1, that is why it is n by a. So this is the intensity of the beam, and the number of target nuclei in the foil. What will be the number of target nuclei in the foil? Look, n nuclei per unit volume is there. So this is per unit volume. So if you multiply with the volume of this, what will be this? A is the area, delta x is the length. So the A delta x is the volume. So if n is the number of target nuclei per unit volume, so if you multiply with volume, it gives you the number of nuclei, okay, total number of nuclei. I hope this is understood. So we can say, therefore, the number of nuclei transmuted is delta n. This is proportional to these two factors. One is n by a, another one is n a delta x. You can say it in this way. Now you can see a and a, it's getting cancelled, so n delta x. So if you remove this proportionality sign, we have to multiply a proportionality constant, that is sigma. This is the proportionality constant. and as you can see, this A and this A is getting cancelled, so you are left with n delta x. Okay, here sigma is the constant, proportionality constant. And here you can see what is n delta x. What is n delta x? N is the number of atoms, nuclei per unit volume. So if you multiply with delta x, so you see length by volume. So length and length getting cancelled. So number of nuclei per unit area, it becomes, this is the number of nuclei per unit area of the target foil, isn't it? So this sigma is called the cross section. Therefore sigma is equals to delta n divided by n times n delta x. So if you take this n delta x as n1, let's say n1 is the number of nuclei per unit area. So this is delta n divided by n times n1. So what is this sigma? This sigma is known as the nuclear reaction cross section. Mono energetic means what? Mono means what? Mono means one unit. Energetic means energy related to energy. So mono energetic means the particles which have a single energy, means single wavelength. So E equals to hc by lambda, na? So energy is specifying, energy means specifying lambda. So here mono energetic you can say equivalent to monochromatic. It means, let's say if you are sending red light, you will only send red light. There will not be a mixture of red light and blue light. Got it, Murli? Okay, so let's do another treatment. So we don't have much space, but that's okay. We are taking up this kind of thing. Try to understand it very carefully, then we'll go for a problem. So this is the target foil we have. It consists of target nuclei. I'm showing it in this way. Now you are, let's say, sending n0 number of nuclei. This is the n0 number of incident nuclei, and you are getting, let's say, obviously there will be less number of nuclei, say n number of nuclei you are getting, and this target nuclei, let's say this point is x equals to 0, and let's say this is x equals to x, some other value. Okay, so we can write the probability of the incident particle, to interact with the target atom will be equal to how much? If I, let's say, express the probability by P, this will be the ratio of the number of interacting particles number of interacting particles divided by number of incident particles. Simple as that. The number of interacting particles divided by the number of incident particles, the way we define probability. Now let's say dn is the number of interacting particle and n is the number of incident particle. Then what will be our case if, let's say, dn is the number of interacting particles and n is the, for the timing you just forget the numbers. Number of incident particles. Then we can say that probability P is equals to dn by n. Okay. So dn by n, what will be this value? Number of interacting particles by number of incident particles, dn by n. What will be this value? It is like this, dn by n. So sigma into n1. So here from you can see sigma into n dx, you can say from this relation, dn by n equals to sigma times n dx. Just use the previous formula. Red also have range. No, any color particle is defined by a single lambda. It monoenergetic means it is having single lambda. Okay. It may be red, it may be blue. Yes, you are right. So different types of different shades of red may be there, na? You can see this is red and this is reddish, some other kind of red. So obviously these lambdas will be different. Like in the pink, you see pink color, they have good amount of variation, you must have seen. So it is like that. A particular lambda means a particular energy. Monoenergetic means having only one value of energy. Okay. Therefore, if we take the integration of dn by n is equals to, let's say, minus sigma n x equals to 0 to x, and here let's say the probability dn by n, here the integration is, let's say, n0 to n. I have no space. Okay, let's evaluate this integration. We are doing it here. So the left hand side will give you ln n upon n0, and the right hand side is giving you minus sigma n x, and from this you get n is equals to n0 e to the power minus sigma n x. So this relationship gives you the number which are decreasing with x. You can see if you send, let's say, n0 number of particles here, if you send n0 number of particles here, after x distance it will be this. It's exponential decrease, and there may be on this side. Tell me if you have any question. It is like, let me tell you how it is. Let's say n0 number of particles are there. I'm taking an example so that you understand it better. Let's say you send 500 particles. Okay, out of those 500, let's say 100 is interacting with this atomic nuclei. So the remaining 400 will be n, that is undergoing without any nuclear reaction, they are passing. Okay, so n0, let's say 500, let's say 100 nuclei has undergone nuclear reaction, so remaining 400 is represented by n. And with distance, how n is decreasing, how incident number of particles are decreasing, that is shown via this relationship. So it decreases exponentially. Okay, did you understand this fact, simple fact? N is equals to n0 e to the power minus sigma nx. So this is deteriorating or attenuating exponentially. You send 1000 particles, let's say 300 interacted or undergone nuclear reaction, then the remaining 700 will be n. Clear? Tell me, then we'll go for the problem. Look at this problem and do. A beam of proton of certain energy equivalent to a current of 1.6 milliampere is incident uniformly on a 56F target containing 10 to the power 22 atoms per meter square, so that the following reactions take place. If cross section for the reaction is 1 bar, what will be the number of neutrons produced per second? Read the question and try to do this. A beam of certain energy equivalent to a current of 1.6 milliampere. From this you can get the number of particles, because I is equals to dq dt. So I is equals to, you can say, q by t. So I is given, you can find out q. Q is equals to ne. So from that you get n. The beam of proton energy is equivalent to 1.6 milliampere is incident uniformly on a 56F target. 56F नहीं FE होगा iron. And the target containing 10 to the power 22 atoms per meter square. Atoms per meter square means this is n delta x, है ना? So that the reaction takes place. If the reaction cross section means sigma is given, what will be the number of neutrons produced per second? So what actually it has asked, let's say if you have sent n0 number of particles. Look, one proton is producing one neutron. So what will be the number of neutrons produced? You can see if on this side, if you get n number of particles, so you have sent n0 and you are getting back n, it means it does mean that n0 minus n number of particles has interacted, and the number of times they interacted they produce n number of one neutron. Okay, so actually it is the number of neutrons produced. One reaction means one neutron. So what will be the number of neutrons? Obviously this is n0 minus n. So this is asked. Understood the question now? Everything I have just mentioned, you just need to find out the answer. Ajay, are you there? Why are you silent? (56) Fe plus P is equals to 53 cobalt plus neutron. So one proton is having nuclear reaction with the nuclei and producing one neutron, and it contains 10 to the power 22 atoms per meter square. Means n delta x means nx, you can say. I 1.6 milliampere, 1.6 into 10 to the minus 3 ampere, since Q is equals to IT, Q by T is equals to I. And that means NE by T is equals to I. Number of particle incident per unit time. Per unit time, if you write, what will be this? N0. Look, per unit time, N by T, I by E, N by T is equals to I by E. I is given to you 1.6, capital में लिखे हैं, चलो capital. So 1.6 10 to the minus 3 divided by electronic charge 1.6 10 to the power minus 19. So this becomes 10 to the power 16. This is per unit time, so its unit will be per second. So n0 we have got. Now to find out n, what we can do To find out n, we can use this formula n0 e to the power minus sigma nx. Okay. Therefore, the number of particles which have which interact with the target is n0 is sent, you got back n, it means n0 minus n number of target, n0 minus n number of particles have interacted with the target. So it is n0 minus n is equals to n0 e to the power minus sigma nx. So this is n0 into 1 minus e to the power minus sigma nx. So this is equals to n0 1 minus, okay, this is what you need to find out. What is n0? N0 is the number of particles you sent, so that is 10 to the power 16. 1 minus e to the power minus sigma is 1 barn is given, sigma is equals to the cross section of the nuclear reaction is 1 barn. So 1 barn is 10 to the power minus 28 per meter square. Let's say multiplied by nx. Nx is what? 10 to the power 22 atoms per meter square. So here it is, atoms 10 to the power 22. Because sigma is given to you as 1 barn 10 to the power minus 28 meter square, and nx is equals to 10 to the power 22 number of atoms per meter square. So meter square getting cancelled, you see. So this is, if you do this calculation, you will get approximately 10 to the power 10. This is the number of neutrons produced. Number of neutrons produced per second. Clear? This is matching with option. The next part of the lecture is a little bit theoretical but conceptual about nuclear force. We have already talked a lot about nuclear force. Now we are dedicatedly will do or cover this nuclear force topic. Small topic. You need to know few things about nuclear force. Basically the properties of nuclear force. Can you tell me some of the properties of nuclear force which I have told during this course? Tell me, everybody, tell one property of nuclear force. Let's see how many are matching with the property we are going to share. Just write down whatever you know. What are the properties of nuclear force? One by one. Ajay, Harry, Murli, write them out. Charge independent, okay, very good, means the interaction between proton neutron or proton proton and neutron neutron are same. Another, let's start with the basic thing, na? Short range, good. It's a strong, interacting or repelling. Short range is a good property. Any other property? Strong and short range, very good. Other than that, charge independence, Murali has mentioned. So other property. Depending, okay, you can tell me the property which is related to like one nucleon and one proton is not interacting with the further proton or neutron. It is only interacting with its neighbor. What is that property called? Spin dependence. Good. I'm just giving a hint. So three property almost done. I am telling you the property. You have to name that property. Okay. This nucleon only interacts with its neighbor. They don't interact with further nuclei. What is this property called? This is one of the most important property of nuclear force. Like the nucleons only interact with its nearest neighbor. What is this property called? Have you heard this property, nuclear force gets saturated? Saturation property of nuclear force. What is that meaning? This is the meaning, right? That nucleons will only interact with its immediate nearest neighbor. Will not interact with the further nuclei. This property is the saturation property, saturated force. So nuclear force is a saturated force. So let me just read it out. The basic properties of nuclear force. The first of one, it is a strong attractive force. This is the best feature, most important feature. Nuclear forces are fundamentally strong and attractive, ensuring that protons and neutrons are held tightly within the nucleus, overcoming the repulsive forces between the like charges. Like charges means proton, proton, or neutron. Neutron is chargeless, so you don't need to worry about it. Actually talking about proton, proton. Number two is short range. These forces operate effectively only within a very short range, around 1 to 2 femtometers, meaning they diminish quickly beyond this distance and have no significant effect outside the nucleus. And the third property which I asked you is saturated forces. Nuclear forces are saturated, meaning each nucleon, proton or neutron interact primarily with its immediate neighbors, not with the distant nucleus, leading to a stable structure. So this kind of questions are a little bit tricky. Okay? So this kind of question you may be asked in the examination. So whenever you see this is little unusual thing. Saturation, how do you guess that it is talking about the immediate neighbor? So this type of thing you should be thinking critically, and you should keep it in mind so that you can answer it in the interview. Fourth property you have already mentioned, charge independence. Nuclear force acts similarly between pairs of nucleons, neutron-neutron or neutron-proton or neutron-proton-proton, indicating that they are independent of electric charge. Number 5 is the non-central force. Unlike gravitational electric force, which are central. Central means what? It is proportional to 1 upon r. Whether you have seen gravitational gmm by r square, electrostatic force 1 by 4 pi epsilon naught q1 q2 by r square. So you see it is a function of distance. Okay, no? I should not write 1 by r. It is, you can say the force is a function of this r, central force. Nuclear force is not like that. Nuclear force depend on factors beyond just the distance between the particles, such as particles orientation and speed. So this is non-central. Nuclear force is not only depending on r, it depends on some other factors. So this non-central aspects of the nuclear forces allows for various spatial arrangement of nucleons within the nucleus. So remember this, nuclear force are non-central. Intensity compared to other forces, nuclear forces are extremely strong, approximately 10 to the power 33 times stronger than electromagnetic forces. 10 to the power 33, can you imagine? And 10 to the power 35 times stronger than the gravitational force, which holds the planets. Okay, so you see, this nature is so strange. If you consider an atomic nucleus, its dimension is so tiny. You see, of the order of femtometer. You can imagine. The kind of force which is acting inside the nucleus is 10 to the power 35 times. It is not like it is 10 times or 1000 times or 10,000 times or 1 crore times. It is 10 to the power 35 times stronger than the force which are holding the planets and stars. So nature is beautiful, nature is strange, you can see. Spin dependence with tensor components. Nuclear forces vary with the spin orientation of the nucleons. It means like proton if they are aligned in this way, okay, they are aligned proton neutron or neutron in this way, they are aligned. So nuclear forces vary with this orientation also, include tensor components as seen in the Deuteron. We'll talk about Deuteron today itself, and you will see that it is a bound state of proton and neutron. We'll have a complete discussion on Deuteron today, showing that the force is affected by nucleons spin alignment. Spin alignment is very important. Depending on the alignment, you can get singlet or triplet. So singlet means S is equals to 0, triplet means S equals to 1. 2s plus 1, it is equals to 1. That is why the name singlet. And when you consider S equals to 1, 2 into 1 plus 1 is 3. That is why it is called triplet. So any question from this new properties of nuclear forces? Ajay, Hari, Muli. All clear? Now there is a theory called the Mason theory or Meson theory of nuclear force, that is also called Yukawa theory. So what is the origin of this strong attraction? So inside the nucleus, as I told you, nuclear force holds the nucleons together at a very strong manner. So what is the origin of this strongness? So why it is so strong? So a theory is there regarding this, which is called the Meson theory of nuclear force, also known as Yukawa theory. So as per this theory, this theory was also known as Yukawa theory, was proposed by Japanese physicist Hideki Yukawa in 1935 to explain the strong nuclear force that binds the proton and neutrons together. So they suggested these two things. Firstly, nuclear force originates from meson exchange. Okay, nuclear force arises due to the exchange of particles called a meson. Mesons we have already introduced in the particle physics lecture, pi meson. Between nucleons, these mesons have non-zero rest mass, which help to explain the short range nature of the nuclear force. So it is actually the pi mesons which acts as the mediator. Yukawa proposed that the meson responsible for the nuclear force are pi mesons, which comes in three types: pi plus, pi minus, pi 0. The exchange of these mesons between nucleons create an attractive force. Between, let's say, proton and neutron, mesons are exchanged. So because of this exchange, an attractive force is generated which is strong enough to overcome the repulsive barrier. If I consider, let's say, proton and proton, so they exchange pions, and because of this an attractive force is generated. So instead of the repulsion between two protons, this attractive force is strong enough to overcome the repulsive electromagnetic force between protons, thus holding the nucleus together. Otherwise, if you can see, if you put the protons together, it would have been gone away, because protons are positive, but still how they are getting attracted towards each other? Because of this strong nuclear force. And neutron doesn't have any problem. The only problem is with the proton, but that problem is resolved automatically by the exchange of these pi mesons. So in summary, meson theory describes nuclear force as a result of meson exchange between nucleons, with pions being primary particles involved in mediating this force. So this last two lines summarizes the whole thing. Okay. The Euclid theory basically explains the origin of the attractive force acting between the repelling protons, you can say. Okay, now let me just give you a brief account on different types of potential we generally discuss in nuclear physics. Okay, so from nuclear force it is enough. Now there are a few types of potential which are asked in your examination time to time. The first one is square well potential. We have already talked about it. Let me just reiterate it again. Square well force, how does it look? You see, whenever we will do particle in a box problem, you will see this kind of square well potential. So this is your zero level. This is minus V naught, and this shows that we are inside the nuclear radius. So this is a rectangular potential well. So this potential V of R versus R, it is mathematically represented in this way that V of R is equals to minus V naught when the radial coordinate R is less equals to R naught and it is 0 beyond R greater than R naught, where R is the relative coordinate of the two nucleons. So what actually these potentials are? Look, as in case of electromagnetic theory between the charged particles, we know exactly the potential form of the potential. It is proportional to, is a function of R, you can say, as I told you. But for nuclear force, we do not know. Right? It may be function of R or some other non-central part may be there. So nuclear force is in general non-central. That is why to discuss or to understand the exact nature of the nuclear force, scientists give different model, and in the process of proposing different models, they have introduced various kinds of potential. So we are discussing one of few of those potentials which are quite important. So you must have seen this potential in the discussion of cell model also. Here we are separately just focusing on those potentials. Okay. B naught is the depth of the potential. Parameter R naught corresponds to the range. Okay. Achha, to make it familiar with you, let's rewrite this R naught as a capital R, the nuclear radius. You know, range is the radius now. This is the first one. The next one is very important, that is Yukawa potential. Yukawa potential. You just need to remember the mathematical form and the graph we have. U potential is given by V is equals to minus V naught e to the power minus small r by capital R divided by small r. R is the range of the nuclear force. Range of the nuclear force. That is, it is talking about the radius, no? U potential. Another one is Wood suction potential. Wood suction potential has this form V is equals to, and this Wood suction is the best one to describe the nuclear force. This is minus V naught upon one plus exponential minus R minus R naught or R capital R divided by C is some constant related to nuclear radius parameter. This is your zero line, right? This is V, this is R. So it is just the modified form of the squirrel potential. इसका इस साइड का पेट मोटा हो गया. So this lower level, what does it represent? Minus V naught. You can see if you put R is equals to 0, R is equals to 0, what will have? Minus V naught. And look this one. here it is minus V naught by 2, and this corresponds to capital R, range of the potential. Is it clear? Instead of C, you can also write it as A. Which of the following function describes the nature of the interacting potential VFR between two quarks inside a nuclei? R is the distance between the quarks. A and B are positive constant in the suitable dimension. A is, if you remember, we have talked about thickness parameter. T is equals to 4.4 A. So A is that thing. A is a constant. If you want to write about A, is called diffuseness parameter. Value is typically around 0.5 femtometer. Actually, this diffuseness actually determines the sharpness. The sharp, it transit from inside the nucleus to outside the nucleus. As you can see, we consider it to be R. So here it is not exactly sharp. So this A factor gives you how sharply it transit from inside the nucleus to the outside the nucleus. Only B option is correct. Yes. Why B option is correct? You see, when you consider two quarks, two types of force is attracting is applying. One is the strong attractive force because of the nuclear force. Another one is the repulsive force due to Coulomb. Okay, na? So attractive force is represented by negative sign. So negative is there. Repulsive force is positive. So plus BR. Only this option is matching. Here both terms are repulsive. Here first term is repulsive, second term is attractive. Here first term is attractive, second term is also attractive. Okay. So option B is the correct option. Minus A by R because this nuclear force is short range force and decreases with decreasing distance. So that is why option C is not correct. Option C is not correct. You can see if you consider this to be attractive, it is proportional to R. But you know, for nuclear force, it dominates with R. So that is why B is more appropriate. B is appropriate. Distance, DANC, because nuclear force will be of repulsion type at long range. Clear? So this is the plot, like kind of hyperbolic plot we have, rectangular hyperbola. This kind of graph, you know, is called rectangular hyperbola. I think you know it. It is not about the formula, it is about the sign. You must have seen that when your force is having a positive sign, it is of the repulsive. This we can say is repulsive. And when your force sign is negative, we can say it is attractive. So here it is minus A by R, so it is attractive type, and BR plus is there, so that is what is repulsive type. So you can understand it in this way. Let me just, if I draw it in this way, let's say V of R. So when you consider the small value of R, then this attractive one will be dominating. So that is why you will get a behavior like this. Okay, na? So minus A by R. When R value is less means the nucleons or the quarks are closer. Okay, na? And as you keep on increasing R value, so it is slowly takes the form of B. It is a kind of linear form in this way. So for large value of R, it is taking this value. So you can imagine that when this is the R value, a low R value, for that it is attractive minus A by R, and as you increase R, it becomes repulsive VFR. Nuclear force will be of repulsion type at long range in this way. Is it now completely clear? Okay, so let us dive into Deuteron problem. Okay, चले Deuteron problem पे. It is more of informative. Deuteron problem, you need to remember few things. Okay, Deuteron problem is not like a many mathematical topic. It is more of informative topic. So you need to have the information about this Deuteron. Deuteron is what? It is the isotope of hydrogen, you know, 1H2. 1H2 means it has Z is equals to 1, N is equals to 2 minus 1. So it means it has 1 proton and 1 neutron. Okay. This 1 proton and 1 neutron, they remains bounded inside the nucleus, and this is a deuterium nucleus. Deuterium atom, but deuterium nucleus. Understood? When you talk about nucleus, it is deuteron. Deuteron nucleus. And when you talk about the atom, it is deuterium, because it only also has 1 electron, right? So nucleus plus electron makes up the atom, so that is deuterium. Understood the difference between deuterium nucleus and deuterium atom? A deuteron 1H2 nucleus consists of a neutron and proton. A neutral atom of 2H is called deuterium. It is the simplest bound state. That is why this deuteron is discussed individually. It is the simplest bound system of nucleons, and therefore gives us an ideal system for studying the nucleon-nucleon interaction. Inside this nucleus, only 2 nucleons are there. So it becomes easy for us to study the nature of interaction between 2 nucleons. That is why this is the most important, nucleus. An interesting feature of the deuteron is that it does not have any excited state, because it is a weakly bound system. It exists only in the ground state. Why there is no excited state? Because if you want to take up the excited state, you need to provide energy. Now if you provide energy, this proton neutron bond will be broken, so it will get disintegrated. So you will not have the existence of the atom or nucleus. That is why there is no excited state of deuteron, only ground state exists in a ground state, and only 2 nucleons are there, so that is why it is weakly bound. So you got the basics of deuteron. Now let's talk about the kind of binding energy which acts between the proton and neutron. So we can make use of the Einstein-Summers mass energy equivalence law, E equals to mc square. So for proton, the mass is 1.67 10 to the minus 27 kilograms. So mc square, if formula if you put, you get energy value of 1.50 10 to the minus 10 joule. And in terms of the MeV unit, you see proton mass is represented at 938.3 MeV per c square, and neutron mass is 939.5 MeV per c square. So you see there is a mass difference between proton and neutron. Neutron is slightly heavier than proton. So if the deuteron nucleus contains both proton and neutron, so if you add their masses, what you get? 938.8, 938.3 plus 939.5. So if you add them, so 1860 and 70, 77.8. So 1877.8. Okay, this is the individual masses, right? You can imagine it in this way. Proton mass is 938.3 MeV, neutron mass 939.5 MeV, and when they are forming this nucleus, deuteron nucleus, its mass it should have been 1877.8, but here the mass is 1875.6 MeV. So if you add them, you get 1877.8 MeV. So you can see some amount of mass has been disappeared, 1877.8 MeV minus 1875.6 MeV. It has been lost while forming the deuteron nucleus. So this amount of energy will be the source of binding energy between this proton and neutron. So this comes around 2.2 MeV. So this is the source of binding energy. Source of binding energy between the proton and neutron. So the mass of the deuteron is this: mass of proton plus mass of neutron minus the binding energy. Is it clear till now? This is actually the main slide of deuteron. Crystal clear, very good. Now there are certain very specific properties of deuteron nucleus that you need to know. First of all, binding energy we have already talked about. Deuteron's binding energy, as you can see, it is 2.226 plus minus 0.03003 MeV. So we have seen it in a 2.2 MeV. So precisely it is 2.226 MeV plus minus 0.00. This is the error. You know? Error value 0.003 MeV. So you remember this 2.226 MeV or 2.2 MeV, you can remember, indicating the energy required to separate the neutron and proton. This is the first property. There exists some binding energy. The magnetic moment value mu d is 0.85735 plus minus 0.403. This is in terms of nuclear magnetons. This is the error value. You need to remember this value 0.85735. It is showing that it is not 0. Okay, this small value, it shows that it is not exactly 0, but it has some finite positive value 0.8573. One nuclear magneton, it is represented as Nm, not nanometer, it is nuclear magneton. Eh cut by twice mpc. This is written in CGS unit. In SI unit it will be Eh cut by twice mp. The magnetic moment of deuteron is 0.85735. Now the electric quadrupole moment value we have already talked about when we discussed electric quadrupole moment. We have seen that deuteron nucleus is a prolate nucleus. So its charge is extended along the symmetry axis, right? If you remember, we called it a prolate structure, right? In this way. So prolate, it means it has a positive value, you can see plus 2.82 10 to the power minus 27 10 to the power minus 27 centimeter square, indicating that it is a slight deviation from its spherical symmetry. For spherical symmetry, what you have, kq is equals to 0. It has positive value, means it will be roulette in nature. Now let's talk about the spin parity. What is the spin parity? J is the spin, pi is the parity. It is 1 plus. Remember this, 1 plus. With 2s plus 1 is equals to 3, the Deuteron exists in a triplet spin state. Total spin s is equals to 1. Can you tell me how 1 plus is coming? Anyone? Harry? Where from this 1 plus coming? Ajay? I think you can say it, how 1 plus is coming. Which rule we can use to get it 1 plus spin parity value? Odd case. Very good. So we have to use Northam's rule, right? Z is equals to 1, n equals to 1. So Northam number Jp minus Lp plus Jn minus Ln. This was the formula. Correct me if I am wrong. So Z equals to 1 means it is 1 as half, right? 1 as half 1. So L is equals to Lp is equals to 0, Ln is also 0. So it is, you can see, half minus 0 plus half minus 0, it is 1. Okay, so this is the J value, and parity is minus 1 to the power Lp plus Ln. So this is plus 1, so that is why it is 1 plus. Clear? So spin, if you take 1, it is 2s plus 1, 3. So that is Deuteron exists in a triplet spin state. Isospin of the Deuteron is 0. It is not like pions, like it exists in 3 multiplets, pi plus, pi minus, pi 0. It is not like that. It is only one Deuteron. That is why the isospin is 0. It is a combination of neutron and proton without isospin excitations. Number 6, binding force characteristics. The force binding the neutron and proton within the Deuteron is neither electromagnetic nor gravitational. It is a nuclear force of different origin that is strong enough to overcome the repulsive forces between the particles. Now, symmetry and spherical structure. The difference between the magnetic moments of the proton, you see, we got mu d non-zero, right? Mu p plus mu n minus mu d, it is non-zero. Remember this one. We have proton, so proton will have mu p. We have neutron, means neutron will have mu n. We have the deuteron, so it is mu d. Now it has been observed that mu p plus mu n minus mu d, it is not equals to 0. It should have been 0 like this, but it is not 0. That is what it is being described here. Mu p plus mu n minus mu d is not equals to 0. It suggests that the Deuteron does not have a fully spherically symmetric 3s. Whenever you have S state corresponds to L is equals to 0. L is equals to 0, this corresponds to spherically symmetric. Okay, spherically symmetric. If only S state is there, it would have been spherically symmetric. But this non-zero value suggests that it is not fully spherically symmetric. So in addition to this S state, there will be another thing. So it doesn't have a fully symmetric 3s1 state. The Deuteron wave function also has a small admixture of 3d1 state, although small, but it will remain. It is like 96% of this thing and only 4% of this, like this. So you can represent the wave function in this way: a0 psi 0 plus a1 psi 1. So a0 gives you a0 square, gives you the probability of being in the state psi 0. a1 square gives you the probability of being in the state psi 1. So if you take a0 square, it will come around 96%, and if you calculate a1 mod square, it will come around 4%. We'll talk about it later also, don't worry. For the timing, you know. Spin dependence and potentials. The forces in the NP system are spin dependent, and the neutron potential is non-central, contributing to the observed characteristics of the Deuteron's ground state. So you can see this, meaning both are in opposite direction, means S equals to 0. Both are in opposite direction, S equals to neutron, proton, neutron, proton. But when neutron, proton are having same alignment, it is S equals to 1. So that gives rise to triplet. So this is the case of Deuteron. The ground state of the Deuteron has unique nuclear properties that arise from the interplay of its binding energy, spin parity, and quadruple moment, all of which indicates a complex structure not fully described by simple spherical symmetry. Simple spherical symmetry is not enough to address all the properties observed from the Deuteron nucleus. Now we'll talk about this thing which is mentioned in point number 7. This is most important for this Deuteron. Many times questions came. So let's address this point number 7 separately. The wave function of the Deuteron. So if you look at the wave function of the Deuteron, it is a superposition of two quantum states. One is the 1s or spherical, and 1d is the non-spherical state. S state is the spherical state, D state is the non-spherical state. And as a result, the wave function is represented by this. It's very important. Psi is equals to a0 psi 1s plus a2 psi 1d. If you write it in terms of bracket notation, you can write it in this way. This is in terms of the bracket notation. D is excited state or not? No, all of them are grounded. It is like in the ground, this psi is the ground state, okay? Psi is the ground state, and in this ground state, Deuteron, let's say it is like ground state. It is consisting of two rooms, okay? So room 1, room 2. Now Deuteron, let's say consider it like a person who spent 96% of its time in room 1 and 4% of its time in room 2. It's like that. You can imagine it in this way ki, you are living in a room, one is the dining room and another is the living room. So you are living for 96% of the time in your living room, and only when you require to eat or something, you are going to another room. So 4% of the time you are staying in that room. It is like that. Psi 1s is the wave function corresponding to the S state, orbital angular momentum L is equals to 0. Psi 1d is the wave function corresponding to the D state, orbital angular momentum L equals to 2, which has a quadruple moment and is not spherically symmetric. So this is an admixture of 1s, 3s1 and 3d1. Why 3? You see, s is equals to 1. So 2s plus 1 is equals to 3. That is why we have 3s1 and 3 d1. These are the twists. Yes, Harry, Paul's exclusion principle. I will check about it. That question also came into my mind, which you are asking, but I think this is nucleons. We are talking about the nucleons, not the electrons. Pauli gave this Paul's exclusion principle we used for electrons, right? Okay, I will check, Harry. What is the actual case for this here triplet state? I'll share it in the group if I get an answer for that. Yes, I understood your question, Harry. I have to find the answer. It may be either these pictures are not correct. Okay, it is capital S. So it is taken in this way. Say S1 is equals to half, S2 is equals to half. Where S is between S1 minus S2 to S1 plus S2. So the combined spin is either 0 or 1. Okay, this is actually the concept. This visual representation may be wrong. This S is the total spin. Yes, let's move forward. If I get that answer, I will let you know. For the time being, this is the one for proton, it is spin half, for neutron is spin half. So the S spin algebra gives you S1 minus S2 to S1 plus S2, that is 0 and 1. And for Deuteron, this one is the case, triplet state. The square of the coefficient A0 square and A2 square gives the probability that the deuteron is in the S or D state. A physical interpretation of the wave function. Deuteron is primarily found in the S state because A0 square is equals to 0.96, meaning 96% of the time it is in the L is equals to 0 or spherical state. However, there is a small probability mod of A2 square equals to 0.04, it means it occupies 4% of the time in the D state. L is equals to 2. This D state contribution indicates that the deuteron is not perfectly spherical as a pure S state. So most of the time it will look like a proper sphere, but 4% of the time it will look non-spherical. What is the significance of the mixture? Experimental values of the deuteron's electric quadrupole moment and magnetic dipole moment can only be explained if the ground state is not purely S wave. If it is purely S wave, what should have been the quadrupole moment? It should have been 0. But we got a non-zero value of what was the quadrupole moment value? We got the value of plus 2.82 10 to the minus 27 centimeter square. So this is a proof. The positive value is a proof that it is the ground state is not described by purely S wave. And also the magnetic dipole moment value, it is non-zero we have got. It means in addition to S there is something else. The presence of the D state in the wave function contributes to the electric quadrupole moment, reflecting an asymmetry in the charge distribution. This mixture of 3s1 and 3d1 states lead to a slight deformation, explaining why the deuteron has a quadrupole moment despite mostly being in an S state. Now, as we have seen, this is a nucleons, proton and neutron, so that will also have some potential well. So what is the range and depth of that potential of deuteron? So you see, the range and depth of the potential, it has a relation like this: V naught R naught square approximately h cut square by 4m, where m is the mass of the proton or neutron and R naught is like is the range or radius, you can say approximately 2 femtometer, effective range of the nuclear force acting within the deuteron, and V naught is found out to be 36 mega electron volt, depth of the potential well for the deuteron. So this relation you need to remember: V naught R naught square is equals to h cut square by 4m. R naught is 2 femtometer. Okay, now this is the last thing. This graph shows the potential well has a depth of minus V naught. So this depth is responsible for the attractive force between the proton and neutron. Because of this depth in the potential, the proton and neutron are bound together. And you see this minus 2.226, what is that? This is the nuclear binding energy. Binding energy of the deuteron is minus 2.226 mega electron volt, which is the energy required to separate the protons and neutrons. Proton is there, neutron is there, and the force acting between them is 2.226. So if you apply some force which is more than this, if a gamma ray of energy at least 2.226 MeV is applied, it can supply enough energy to overcome the binding potential, disintegrating the deuteron. So if you send some, let's say 4 MeV particle to the deuteron nucleus, what will happen to it? It will disintegrate. R naught is equals to 1.2 Fermi here. No, it is actually the range. It means it is like this nuclear size. This R naught is creating problem. It is like the radius. Instead of writing R naught, you can write capital R. This is the effective range, not the nuclear radius parameter. I am just writing it here. The same R we used in the case of nuclear force. And R is the range of the nuclear. So it is more than 1.2 femtometer. It is like range. If you consider, if you measure it from here, range is like this. How much range it has? And if you imagine it, r is equals to r naught, it is the power 1 by 3. So it is, you can say, slightly greater than r naught. So it is not exactly 1.2, it is more than 1.2, because a will have some value. So for this you can say, if I now this question has been given separately. Bound excited state for the deuteron are not possible. Deuteron is a bound state of proton and neutron, has only one bound state with binding energy approximately 2.226 MeV. This is primarily the mixture of 3s1 and 3d1. Same thing has been talked about. A lack of bound excited state is due to the nature of the nuclear force between the proton and neutron. The strong nuclear force is short range and is very specific structure that does not support higher bound energy levels. Any additional energy input would exceed the binding energy, leading to the disintegration of the deuteron into free nucleons rather than forming a bound state. If you try to higher up this, make it higher, the energy, it will not go higher, but it will disintegrate into free proton and free neutron. That is why bound excited state does not exist for deuteron. Now let's do some problem. The ground state wave function of a deuteron is in a superposition of S and D states. Which of the following is not true as a consequence? A, B, C, D. Which one you think? Not true as a consequence. The orbital wave function is not spherically symmetric. So this is true, na? If it is spherically symmetric, then it would have been only S, but there is a mixture of S and D. It means it is not spherically symmetric. So this is the conclusion you can draw from it. D, yes. So option D. You see, it has non-zero quadrupole moment. This is the inference or conclusion we can make from this statement. Non-central. This also we can say, because if this were spherically symmetric, then you could have said it is central, but S and D, so non-central. So this fourth point. So I have added explanation for this. The ground state of the deuteron is indeed though. Is a superposition of S wave and D wave. The superposition leads to several consequences. Firstly, it has a non-zero quadrupole moment. This is because the D wave component, it has slight quadrupole moment. Secondly, neutron proton potential is non-central because of the presence of the D wave. Orbital wave function is not spherically symmetric. All of these because of the additional presence of D wave component. D is not true because Hamiltonian of the deuteron system does not conserve total angular momentum. Deuteron ground state has a total angular momentum A equals to 1, which is conserved. Next problem. Which of the following statements is not correct? This kind of statement based question you can expect in your examination. This is not correct. Deuteron has no electric quadrupole movement. So you can look at it as these explanations. Deuteron can be disintegrated by irradiating it with a gamma ray of energy 4 MeV. This is correct because the binding energy is 2.2 MeV. So more than 2.2 MeV can disintegrate the proton and neutron. Deuteron has no excited state. This is also correct. It has only one bound state, that is the ground state, and no bound excited states. Okay, no bound excited states. Notice this line. Deuteron has no electric quadrupole moment. This is incorrect because it has a small electric quadrupole moment because of the admixture of d wave component. 1s0 state of deuteron cannot be formed. So here you see this is 1s0. 2s plus 1 is equals to 2 into 0 plus 1 is equals to 1. So this is not possible. Singlet space with total spin 0 cannot exist for the deuteron because the neutron proton system is a bound state, prefers a triplet state to satisfy the requirements of the nuclear force that binds them. Okay. But the Pauli's, what about Pauli's exclusion principle here? Look, what does Pauli's exclusion principle say? There cannot exist two electrons in a particular subcell, right? With all equal quantum numbers. But inside the nucleus, the situation is different. Okay, I'm not going to comment on this. I will first check, I will verify, then I will let you know. Okay, this anomaly. Okay, let's do this problem, the final problem maybe. Yes, this is the last question for today. Do it. Consider the scattering of neutrons by protons at very low energy due to nuclear potential of range R0, given that this value this shift is. So it is not exactly nuclear phase form. It's a mathematical problem, a simple thing. Do it quickly. Look at this. You know one property. What is the value of tan theta? If you consider very small theta, tan theta can be approximated to theta, right? So cot k r naught plus delta you are given, and this is the scattering of neutrons by protons at very low energy. Okay, so remember this expression. So we'll convert it into tan of this k r naught plus delta, then we'll equate it to theta. Consider the scattering of neutrons by protons at very low energy due to nuclear potential of range r naught. Cot this is given to you. So from this you can find out 1 by tan. So it will be just reciprocal minus k by gamma. So tan theta is approximated to theta. So k r naught plus delta, so the minus k by gamma. So delta is equals to minus k by gamma minus k r naught. So this is matching with option E. So look, in your examination also there will be few questions which will not be from any theory. It may be in the packaging of a particular theory, but many of the time those questions can be solved by using simple mathematics. It will be written in the form of a topic which is given in the syllabus, but it may not have any relationship with the concept. Sometimes you may be able to do that problem by simply using mathematical logic. Sometimes you can do expansion in Taylor series and you can get the answer. You can make some approximation and you can get the answer. So CSIR-NET exam is such an exam. You see, you must have seen many MSc semester 1, semester 2 students crack, because their smartness is little bit higher. Here, in addition to knowing things, in addition to covering syllabus, you need to have also some smartness. Then even without completely covering the syllabus, you can crack this exam. And many times it happens that students cover the whole syllabus, but still they are not able to crack, because they don't have that much of intelligence. Okay, the smartness, that smartness will come if you practice more questions. Okay, so I will request to all of you to practice questions or give test from the test series. I think all of you have been added to the test series. It's the high time we start the test series. We have approximately 2 months or 1.5 months depending on where the examination will be. So start giving the test series. It may appear to be difficult, but keep on doing it, and that will strengthen your numerical ability, and that is most important. That is the ultimate thing you require, numerical ability. Okay guys, start giving test in the test series. There we have new questions. Okay, those are not in the previous year questions, so and those are new questions and good questions. The questions have been prepared in such a way that your effective syllabus is covered automatically through problems. Okay, anyways, we are ending the session here today. I hope you find this session useful, and we'll continue from here. Maybe the next topic will be, okay, nuclear fission and fusion are left, na? So maybe nuclear fusion and fusion. I will check and we'll do that one. After completing nuclear physics, we'll be going to the most important topics. So we'll cover first the remaining most important topics, then we'll come back again to this detailed course. Okay, bye. Take care.